Okay, so this is the feedback for the stable isotope parts of the practical geochemistry and data analysis exam. So this is a video that's going to be focusing on question 4. So just click onto the exam mark distribution. So it says question 2 here, but that's because the way I submitted the marks, not the marks, the questions to the exam thingy, what do you call it, the exam paper. This question we're going to be looking at here was question 3, I think, on the exam. So this is the one in the blue here. So there's a wide range of marks that people got for this. So some people did very well, very well indeed in some cases, which is great. Some people not so much. So we're going to be looking at what we were looking for in this exam question. Which will help if I start with it. Okay, so this is question 3 of the exam. So it was based around the isotope fractionation between calcium carbonate and water, and how it's used as a temperature proxy. So the question is split up into 3 parts. The first is just asking about what is the theoretical basis for the temperature dependence of isotope fractionation. So this is not actually being very specific. This is just asking quite broadly, why do we get temperature dependent oxygen isotope fractionation, or temperature dependent isotope fractionation of any sort? The second part, part B, goes into a specific little detail of the paleotemperature calculations that one might make. I think we went through this in the practical, so you should be familiar with this. And asked this question about how does salinity influence the isotope fractionation. So we'll look into that. And then the last part, which actually only had a few marks associated with it, what else basically can go wrong with our paleotemperature calculations. So looking at the first part, what theoretical basis for the temperature dependence of stable isotope fractionation. Now, because the question is asking about the use of isotopes as temperature proxies, those are usually systems where we assume that the situation is in equilibrium in terms of the isotope exchange between the 2 phases. Now, so I was expecting answers surrounding basically what are the reasons we get equilibrium isotope fractionation, and then why is that temperature dependent? Now, I realize that that's not actually what the question asks, so the question is more broad. So it would be okay in this case to write down some reasons for kinetic isotope fractionators as well, which is kind of not what I intended, but actually if you read the question, it's broad, so I allowed that to be kind of one of your answers if that's what you gave. But basically, I'm just going to go through some of the things that I was looking for in terms of the equilibrium case. But yeah, here we go. Even if you wrote stuff about kinetic isotope fractionation, that was all right. So if there are, these are just some slides from the lectures, if there is an exchange of isotopes between 2 phases, this example here is from the lectures, which is kind of water and hydrogen sulfide. And these phases could be water and calcium carbonate of oxygen isotopes. The isotopes are not distributed kind of uniformly across all of the phases. There's a preference for heavy isotopes to be concentrated in certain phases, and there must be some free energy that's driving that kind of that preference for the isotopes to be in different phases. Now, that implies then that there must be something that's driving that isotope fractionation, and then also a kind of a counteracting kind of driver, which is wanting the isotopes to be evenly mixed across all of the phases. Okay, so that's the entropy term. So this is the leading into why there is a temperature dependence, because it's the balance between these 2 kind of thermodynamic drivers. We've got some preference of the isotopes to be in one phase or the other, and a temperature kind of influence on the entropy. So we could think about giving more details in our answer if we start to go in for actually why is there any isotope fractionation at all, and then why is it temperature dependent. So we've already touched on a little bit on why it's temperature dependent, but let's go into the why it's there's isotope fractionation at all. Okay, and this is to do with bond energy. So heavier isotopes tend to form stronger bonds, but also those stronger bonds tend to kind of concentrate the heavier isotopes, and that's to do with the change in energy between kind of one bond and another is greater for a heavier isotope than a lighter isotope, so that leads to the heavier isotopes being concentrated in these stronger bonds. Okay, and you could have gone into some of the detail of that, stuff from the lecture slides here, and that would have been great. Okay, the more detail you went in, the more kind of marks that were awarded. Now, some people wrote about kinetic isotope fractionation, and the kind of the loose wording of the question kind of allowed for that. I think the people that went down this route, most of the stuff was correct. There was this kind of missing bit at the end where people kind of got to these relationships between the velocity of any kind of one isotope in a gas or in a diffusion process is temperature dependent, which is good. Some people got to this kind of reaction rates, also a function of temperature. But the last step was really missing, and this was also the case in question 1, is that in kinetic isotope fractionation, the fractionation factor can be thought of as the ratio of these equilibrium constants. I think this also should be H, and this should be an L down here. Sorry, I made that mistake. But it should be the reaction rate of the heavy isotope divided by the reaction rate of the lighter isotope. So in this case, we can rewrite those out here in terms of the Arrhenius relationship for the reaction rates, and then rearrange that so we kind of like bring this, I guess the A's kind of cancel out, and then we kind of think of this as actually, because this is a e to the power of something, we can actually, because we're divided by that, that becomes e to the minus EAH over RT plus E active energy of the lighter isotope. Okay, and that's what we've got basically here. So once we've rearranged that, we can then show that the fractionation factor, log alpha of the fractionation factor, once we've kind of dealt with this exponent here, that is a function of temperature. So the higher the temperature, the closer the fractionation factor to 1. The lower the temperature, the further away it can be. So just that last step in a little bit of mathematical manipulation would have got the super bonus marks, not entirely required to kind of get kind of like a passing grade. There's lots of things such as heavier isotopes, the stronger bonds. Heavier isotopes have lower activation energies, react slower. Those would have been kind of like some of the basic things we were looking for. These kind of details at the high end of the mark scale, which is some people got, which was great. Okay, so going on to part B now. So this was one of the parts of the exam which was, I think, a little bit misunderstood, quite poorly answered. So in the case of Paleoceanic records of sea surface temperature based on oxygen isotopes of foraminifera, how and why does salinity influence proxy reconstruction? Now, some people wrote answers that were salinity has a direct influence on the fractionation factor. Now, there might be a small influence on the fractionation factor, but the way we covered that in the lectures, that was covered in the boron isotope, kind of proxy for pH. So that wasn't quite what I was looking for in this answer. So thinking about rewriting this question in another way, which is one of the things that I kind of asked you to do in some of the revision tutorials. Think about how you can rewrite the question in your own words to kind of like understand what it's kind of asking for. So if we think about how we actually use isotopes as temperature proxies, it's the fractionation factor between two phases. So in this specific example, the two phases, the fractionation factor between calcite and water. Now, from the practical, you'll remember that when we make measurements from sediment cores or from anything kind of from the past, we don't have the water anymore. We only have one of the phases. So in the case of this, we only have the calcite. So we need to make some assumptions about the isotopic composition of the water. Okay, so we need to know, we make an assumption about what its isotope ratio is, basically, and then we can compare that assumed isotope ratio with the measured isotope ratio in the other phase, and that gives us an estimate of the fractionation factor, which is then temperature dependent. We can plug that into a temperature equation and give us kind of like the magic beans. Right, so the thing that this question is driving towards is, how does the salinity of some ocean water, how does that relate to any change of the isotope ratio of that water? Because that will then influence our assumption about the temperature change, or the temperature calculation from the fractionation factor between these two phases, which we only know one and we're assuming the other. Okay, so we need to think about, are there processes that affect salinity and the isotopic composition of water? And this was kind of covered in the lecture where we talked about how ice sheets get their extreme light or isotope composition. Okay, so I guess I've just covered this this spiel about these equations. So we have some paleotemperature equation where we have some fractionation factor is some function of temperature, but we don't actually know the fractionation factor. That's not something we can measure. The only thing we can measure is the isotope difference between two phases. Okay, and we can, if we know that difference, we can plug that into a rearranged paleotemperature equation. But the important thing is that we don't know the isotopic composition of the water. So this might vary. And one of the question is asking, how might that vary with relation to salinity? Okay, and this is where I was going with that. This diagram shows some of the processes that go on changing the isotopic composition of water as it kind of moves through the hydrological cycle. So when we have evaporation from the ocean, okay, that removes preferentially the lighter isotopes because they're less strongly bonded in the gas phase than in the liquid phase. There's also a small kinetic fractionation there as well. And then when we condense that water out of the atmosphere, the condensation, or the rain, is isotopically heavy, or has heavier isotope, more concentrated in the heavy isotopes than the atmosphere that it's condensing from, which leaves the atmosphere even more enriched in the lighter isotopes. And as this kind of atmospheric package of kind of moisture moves towards the northern high latitudes or in towards the interior of continents, it becomes progressively more enriched in the lighter isotopes. So that's what we covered in the lecture. So what I was really asking you to do now was think about what the implications are for these processes of evaporation and precipitation on the salinity of seawater. So this is a graph of what we might expect the salinity of seawater to be. So freshwater is over this end, salty seawater is over this end, and here are some oxygen isotopes. So the average oxygen isotope composition of the ocean has a delta 18O relative to the standard, which is standard mean ocean water of 0. Okay, and it's got a salinity of around 35. Now, what this figure shows is some data from the Red Sea, which is a very hot place where effectively only evaporation is happening. And the process of evaporation increases the salinity and also enriches the water that's left behind by that evaporation in the heavier isotopes. That leads to this array up here, because we're effectively taking water of this composition and removing water that's got a salinity of 0 and this delta 18O of -9. Okay, so in this case, it's just equilibrium fractionation between the vapor and the water. There's not that extra little bit of kinetic isotope fractionation that might take this kind of to -13 mil. Okay, so that's what's going on with evaporation. So we already know that in an evaporative case, we might expect there to be a relationship between salinity and oxygen isotopes. Think about what happens when that water that has evaporated falls back down as rain. So here we've got some data from the tropics. So we've got the Atlantic in blue, the Indian Ocean in kind of teal, maybe, and you might be able to just make out the Pacific in yellow. And we can see here that actually it looks like we've got a mixture of seawater, of salty seawater, and fresh water that's got a isotopic composition of this, some range between maybe -4 and -7. So this is the rain that's falling out of the clouds, that's slightly isotopically heavier than the overall atmosphere, because condensation preferentially removes the heavier isotopes. So that leads to a mixture here. So overall, we can see that there is a broad relationship between the salinity of the water and now the oxygen isotopes. So that's what we were kind of looking. That's what I was looking for in the answer. In that salinity should correlate in some way with the oxygen isotopes of the water. So if we have different changes in salinity, that will affect the oxygen isotopes of the water, which will then lead to a different oxygen isotope ratio being preserved in the carbonate, even if the temperature is the same and the fractionation between the water and the carbonate is the same. So that's what we were looking for, and yeah, so there we go. That's what would have got super mega bonus marks. So the last part of the question was really asking basically what can go wrong with a temperature proxy, or what could go wrong with a proxy. So what factors other than the temperature, in this case salinity, could cause variability in oxygen isotopes. So if we've got this nice maybe down core record of oxygen isotopes and we think we're reconstructing temperature or salinity from that record, what might cause us to be wrong? And the first thing that hopefully you should have thought of is that we could have had some diagenesis. So we could have taken our lovely carbonate. So this is an example of a thin section of a coral. And if we start to grow extra kind of carbonate around the edge of that coral, which you might be able to, it's these extra carbonate around the edge of the coral growing here. So this is the primary mineral. And then once the coral has died, we've had some other fluids passing through it, precipitating these other minerals around the edge. And these will potentially be in equilibrium, isotopic equilibrium, but with water of a different temperature and maybe a different isotopic composition than the original mineral. So if we dissolve up the whole thing, measure that, it will give us the wrong temperature. So diagenesis can affect the isotope ratios that we measure in our sedimentary record. The other thing, we could have a change in the relationship between temperature and our oxygen isotopes. And that could be because we have these different empirical calibrations for the paleotemperature equation for different species. So if we change the species abundance in our sedimentary record, we might end up with a change in apparent temperature that we're seeing. So there are other things as well. We could have errors in measurement, all of those kind of things, which we have a little bit of credit for mentioning. But these were the two main things I was looking for: the diagenesis and the change in the empirical calibration due to different species abundance. Okay, so that's what we're looking for in these questions. Here's a picture of some geochemistry going on, which is pretty exciting stuff. So hopefully this has given you a bit of insight into what we were looking for in the exam questions, a bit about how you might have misunderstood some of the questions and what we were actually looking for. So hopefully this has been informative and useful for you. And if you're watching this next year, this is the kind of stuff that's in exams. Although questions do change between years. So yeah, have fun with the rest of the course. Looking forward to the practical elements of the course, where we're going to be measuring some samples, doing some things, looking at data, and writing some reports, which will be awesome. Right. Off we go. Here we go. Off we go. Bye-bye.